Good morning. Test, test, test. Oh, the microphone in, eh? There we go. Testing, testing. That's much better. Good morning, class. How is everybody doing today? I hope that you're doing well. It looks like it's going to be a absolutely beautiful May day today. Temperatures in the high 20s throughout the day today, with no chance of precipitation. This your weather report from WKRP Radio. That's the weather report by frigging Captain Kirk. How's everybody? Give me some love in the chat. Let me see that there is at least one actual human watching this stream. As you can tell, I'm feeling much better today. Oh, thank you. I'm feeling much better today. I'm still, still working out the corners of feeling better, but this is I'm feeling much better than I was yesterday. So I'm feeling more energetic. I'm feeling more vamped up, some more vibrational. So yes, excellent. Excited for the sweet weather. I know, right? It's like perfect weather for the long weekend. I'm so looking forward to the long weekend. Ooh, that's interesting. I have 6 unique people in the chat, but my concurrent viewership stats show me that only 5 people are watching. So that's interesting. That's, YouTube lied to me. My goodness. Yep. Love a cup of tea in the morning. So... So I expect the top of everybody's radar today is going to be what the heck about this test you say that we're having next week. So I'll do like a quick sort of rundown of what the test is, what you should expect, etc., etc. And then if you have any questions, all 6 of you, then please feel free to ask them once I've finished my initial spiel, because, your question might be answered. So, the test will be held prospectively at 2 o'clock. Actually, let me just, I haven't had a chance to check my email. Let me see if Bookings got back to me. Bookings has not gotten back to me. Of course they haven't. So, Bookings is going to get back to me with a room within the next 24-hour period. When I know, you'll know. I'm guessing it's going to be one of the MDCL lecture halls, because they use those very frequently for testing. So, it's interesting, actually, because of the number of dropouts we've had during this offering, we are actually down to a class size of 58, which is pretty easy to squeeze into most rooms. There's a kind of a very large number of rooms on campus that we could actually hold the test in. But anyway, I asked for ones with outlets, because we need outlets for you guys for your laptops, but you should still bring your you should still bring your so bring your device, bring your laptop or tablet with a keyboard that's not technically a laptop, in my opinion, or whatever your device is, that you do your homework on, bring that, right? Bring your charging device. Make sure you're on a full charge before you arrive at the test room, right? The format of the test itself is going to look very eerily familiar to the assignments. Basically, the test is a special and customly designed Jupyter notebook, in the same way that the assignments have been Jupyter notebooks. Obviously not as long as the assignments, because you have a test duration of 1.5 hours to complete the work in. So this is the first semester that we are moving from a sort of 24-hour take-home test model to an in-person testing model, because, a lot of things are moving back to in-person these days, which is good. I think that's a good thing overall. I think online school was a joke, and I think a lot of people might share that opinion in the crowd. So, basically, it came to my attention that some people were taking advantage of the take-home nature of the tests in order to commit academic dishonesty. So this is partially a measure to tighten that up. So one of the things that you're going to be required to bring to the testing room is your student ID. We have to verify your identity and that the person writing the test is you. So, the TAs and myself will be invigilating. So, essentially, you'll be given a set of questions. You will perform programming tasks, which are, they are definitely not the same questions as you've been asked on the assignments, right? There'll be new problems. But the techniques that you need to solve these problems are the techniques that we've been discussing so far. This is not like a math class where the test is comprised of all of the problems you practiced during the homework, right? This should be obvious to you at this point, but the questions that we give during the assignments, our intention is not for you to memorize those questions. That's not how this class works. This is a class on problem solving, so you'll be presented new and interesting problems. At any rate, if you want scrap paper, you'll have to bring it with you. But yeah, so that's all true. That's happening Tuesday. Are there any questions from the class at this point in time? Is there anything I didn't mention? Any questions outstanding? Because this is the last lecture that we're going to have before the test. Oh, coverage. All right. So test coverage is up to and including however far we get in topic 6. Right? So depending on how far we get today in topic 6, the cutoff point, wherever we stop, that'll be how far we are testing you come Tuesday. 1 week from today. Excellent. Are there any questions? If there are no questions, I'm assuming everybody will get 100% on the test. Just waiting for any questions to materialize. Do we have practice tests in... there's a question. So practice questions. Yes. So if you take a look at Avenue, there are some practice questions for sure. Doop-a-doop. Let me just bring that up. I'll show you. So, if you take a look in, I think it's in, so if you take a look in week 4, or topic 4, there is a practice test in here, which comprises a bunch of programming problems. They don't have solutions, but if you want some practice, oh, I remember Superhero Cage Match. That was a fun one. If you want some practice problems, here you go. These are good practice problems. Official and endorsed practice problems. Coding Bat is also an excellent place. Pardon me. Excellent place for practice problems, Coding Bat. Will the question difficulty be similar to the ones we've seen on the assignments? So it will certainly be more in line with the types. It will be more in line with the assignment 2 questions than the assignment 1 questions. The assignment 1 questions, since we've only covered like some very rudimentary stuff in programming, there's like a hard cap on the difficulty that any question on like the first half of assignment 1 could even be, you know? Like there was a very hard cap on how hard those questions could be. So no, the if you're thinking assignment 1 is like a good touchstone for the difficulty of the test questions, please disabuse yourself of that notion. Assignment 2 will be a lot closer to that. Yeah. Good. Can we use Python Tutor during the test? Yes. So you are permitted to use debugging tools, Python Tutor included. If you want to use, pardon me, if you want to use something like idle or some other kind of debugging tool for Python, then you're permitted to do so. The point of the test is that you can actually program, so when we ask you to program, we are not going to take from you all of the tools that you've been relying on to, verify your program integrity. That just seems cruel. So yeah, you're permitted to use Python Tutor. You are permitted to use the Python documentation. You are not permitted to post your solution or the test questions to third-party websites. So yeah, you're permitted to use that type of thing. Does that make sense? Yeah, Python Tutor is an excellent one. Like, you've seen me use it several times in class. I think it's like a really, really excellent tool. And like, not only do I say it's permitted, I would say Python Tutor is recommended. So Stack Overflow. Now there is an interesting one. So I would say Stack Overflow is permitted for the purposes of reference, but you are certainly not allowed to post your code or the problems to Stack Overflow during the test. That's absolutely off, and I would be very, very careful about direct copying and pasting of any code that you find on the internet, i.e., do not copy and paste do not copy paste any code that you find off the internet. That is plagiarism. However, it's difficult because, like, I also recognize that Stack Overflow is an excellent, in fact, the go-to sort of reference manual for obscure problems, like obscure error codes and that sort of thing. So telling you that you can't use it at all seems cruel, but using its more interactive features, shall we say, is certainly academic dishonesty. Does that make sense? Hopefully. Good. I didn't wait for the response, but I said good anyway. So, let's continue on with our... Get back in there, you. What are they trying to do to me? Jeez. So, continuing on. Functions as objects. So, yesterday we talked about functions, we talked about recursion, we talked about some rudimentary analysis of algorithms. Now let's talk about functions in some of the more interesting things you can do with them. So, in Python, functions are first-class objects. This means that a function can be used in the same way that you would use a number or a variable or a list or a tuple or any other thing that you use inside of a program. Like a function name is an object, right? One of the things that we can do with this is we can pass functions as arguments to other functions. Now, this has the flavor of what we of a different paradigm of languages called the functional paradigm. You know, I would say that my favorite analogy is that Python is a functional language in the same way that an 8-year-old wearing her mom's dress is a businesswoman, or wearing her mom's business suit is a businesswoman. Superficial features like this do not a functional language make. But then again, you know, I'm kind of biased because I'm a Haskell programmer. Haskell is the only purely functional language, and nothing else is functional. Has functional features, is not purely functional. So, anyway. So, what does this look like in practice? Well, one very useful category of operations that you find inside of... not the whole dang file system, geez. One very useful function that you use quite a lot if you're programming in Haskell is the so-called map function. So, how map works is it takes a function and it takes a data structure and it applies the function to every element of the data structure and then returns a new data structure where every element has been replaced by the return result of the function that's been applied to every element. For example, if I wrote a function, def plus 3, takes an argument x and returns x plus 3, you know, and I define a map function, which takes a function f, and it takes some data structure L. I'm going to use a traditional loop because I'm feeling old-timey. While I is less than the length of L, we don't forget to increment the counter. We say that L at I is equal to L at I applied as an argument to f. So one of the reason the reason basically that I chose to use a while loop to do this is, you remember my rule, my golden rule of for loops, that you should never ever modify the thing you're for looping over while while doing this. This is basically me doing my golden rule. Now we don't actually have to return L, because if it's a list, it'll be passed by it'll be an alias of the list, so the changes will show up on the exterior. But if this was a tuple, then we would need to return it. So we have a list. 1, 2, 3, 4, 5, 6. We print L. We apply the mapping. So we map +3 to L. Let's make that L2, just to not confuse the actual and formal parameters. Print L2. There we go. Let's open up a terminal. Bing, bang, boom. Wait, what? No. It's like, that's the edge of my laptop. Like, I have another screen off here that I've got my, like, OBS and the streaming page open on. So, like, I want to snap, but it doesn't snap because that's onto a different screen. But, oh, the woes of being a streamer. So, Python 3, topic 5.py. Name L not defined. Am I using it? Yeah, there we go. All right. Boom. So, we print it first. At first, it's 1, 2, 3, 4, 5, 6. Afterwards, it's 4, 5, 6, 7, 8, 9. The mapping has been applied correctly. Does that make sense? So the important thing to note here... There we go. Have to get the arrow in the right... My finger there. So the important thing to note over there... Notice how the function name is being used without the round braces denoting function invocation. So this is an uninvoked instance of a function, right? It's a function. It's a reference to a function. It operates very similarly to an alias. Python is not unique in its ability to do this. You can do this in C as well, as it turns out. C also supports what are called function pointers. So, the fact that Python does this and calls itself a multi-paradigm language, claiming to be partially functional, could you not apply that same argument to C? And pretty much nobody would be, willing to make the argument that C is a multi-paradigm language. But anyway, my personal gripes aside. So that's how you pass a function to a function as an argument. Good. So, and finally we have the anonymous function, also known as the lambda. This traces a little bit more closely to functional language territory. But, so lambdas are a construct derivative from a very advanced form of mathematics that you've probably never heard of called Lambda Calculus. I'll give you a very brief introduction to Lambda Calculus. So, way back, when the mathematical foundations of computation as a science were being laid in England by two fellows in particular, Alonzo Church and Alan Turing. Alonzo Church was was a logician, and Alan Turing was his doctoral student. So Church invented a model of computation known as Lambda Calculus. So that was Church. Church invented Lambda Calculus. Turing invented the Turing machine, which gained a lot more popularity and more quickly. Basically, Turing kind of won out for a pretty large period of time. Turing's model beat Church's model for a while because it's just a lot more directly implementable in terms of, physical components. And that was kind of the intention of the design as well. It's having to do with tapes and read heads and the ability to read and write to a tape. And, if you have ever seen, an old James Bond movie where they have, all of these computer banks from the 70s, you might notice these great big reels that are, shifting back and forth, at different rates. Those are magnetic tapes that are reading and writing programs. That's basically a Turing machine. But anyway, so while Turing's model of computation was more directly implementable in terms of physical devices, Alonzo Church's Lambda Calculus still maintains a certain degree of applicability. It turns out that you can construct anything that can be computed inside of Lambda Calculus. If you're going to be doing any computer science past past the first year courses, and probably, if you take 1JC3, you'll hear about Lambda Calculus. This is a topic that you'll come to some familiarity with. So, how does Lambda Calculus work? Well, it really only has two operations, right? Operation number one is known as the Lambda Abstraction. So this is argument abstraction, or argument extraction. Essentially, you take an expression, right? You remove from... Basically, you take an expression, right? You expose one of the variables of that expression as a function argument. So this is a function, right? Anything with a lambda out front is a function. So the second operation in Lambda Calculus is argument application. So, if you take an expression like this and you apply an argument to it, it works. It works on substitution in the exact same manner that any other function would, right? Function in kind of the more mathematical sense than the programming sense here. So, this expression here, lambda xy, x to the power of y, the first argument applied would be substituted for x. The second argument applied would be substituted for y. So you can produce these lambdas inside of Python code. Now, you might think it was a little bit strange and weird to have such a small function here. That might not serve any particular purpose, especially if you don't need that operation ever again. So, that's true. We can substitute it for a lambda. Lambda x plus 3. So, by so doing, you no longer require the, you don't require the definition, the explicit definition up top. You can just throw in a function. You don't give it a name, right? So once this line of code is executed, this function definition is lost, right? but it's so short you don't care. So yeah, that's anonymous functions. And I know this is like beyond the scope of this course, but I taught a course in the fall of last year that dealt with Lambda Calculus pretty heavily and explicitly, and I'd like to just show you a couple of the slides from that course, to just in case you're interested, because it's interesting, right? Because you can represent Booleans inside of Lambda Calculus. So in pure Lambda Calculus, you would not have like reference to arithmetic operators. It's just lambdas all the way down. It's like turtles all the way down, right? So it's cool because you can represent true and false in Lambda Calculus using just lambda expressions. So in Lambda Calculus, you define true as lambda t, lambda ft, and false as lambda t, lambda ff. So it's like select the first argument given, select the second argument given. And using that, you can actually create like more complicated expressions to express like Boolean and Boolean or and pairs of Booleans, and you can even express numbers in lambda expressions using a successor function. So I just wanted to show you this, and it's cool. And yeah, there's lots of formulas, but this is a course I taught called Computer Science 3MI3 Principles of Programming Languages. So now you know what course to avoid in the future. Ha ha. Anyway, so that just about concludes our discussion of functions. Any questions before we move on? Any questions? Oh, seems like right now there are 4 people still paying attention in the class, which, oy. Cool. So, the few, the brave, the 4. So let's shift gears now and talk about something a little bit off the wall. And now for something completely different. We're going to talk about numerical computations, which is the topic name. What we're actually going to be talking about is what the heck numbers even are. So, I kind of already talked about this in an earlier lecture, but, you know, it bears repeating because it's very important information. We're going to talk about how the integers are actually stored in your computer via binary representation. Then we're going to talk about floating point numbers, and that's going to be an important topic to pay attention to. And then we're going to talk about some more algorithms. So, just wanted to double check, but is this the last lecture that will be on the midterm? Yes. Yep, this is the terminus. Remember that Monday is a holiday, right? So there won't be that might be an important announcement to make. There's no class on Monday. It's a long weekend. Ha-ha! Jolly good show. Excellent, yes, Mom. So, anyway. Yes. So. So the integers. In decimal representation, we use place value to indicate the power of the base number to multiply against the number in that place value to determine its magnitude, right? When we have a number like 2053, we have 2 thousands, 0 hundreds, 5 tens, and 3 zeros, right? This is how numbers work. In the binary system, it's the same structure. What changes is the base number. So whereas in the decimal system, everything is in base 10, decimal, in the binary system, everything is base 2. So rather than indicating, 2 thousands, we have 1 8, 1 4, 0 2s, and 1 1. Right? We add all of those guys up together, and that gives us the value in base 10. So there you go. The reason that computers work like this, right, is if you reduce the number system down to only having 2 digits, this can be represented by high and low voltages inside of electronic circuitry. So you can actually build circuits that perform these types of numerical computations, which is the whole basis of computing. However, it does require us to use a system of numbering that perhaps we are unfamiliar with. You will notice, I think, that so far in Python, there hasn't been much call for you to program in binary. One of the luxuries afforded by programming languages, as opposed to, bare metal programming, is that you can program in decimal, using decimal numbers, and the computer will automatically convert those to binary for its own internal representations. Very convenient. So, here is a question. So let's get your math suits on. What is the decimal base 10 representation of the following binary base 2 number? I'm asking with a poll. There we go. So the number is 011011. What do you guys think? I know it's kind of risky asking for audience participation when I've got like 4 people paying attention. But maybe I have more people paying attention now that I called people out for not paying attention. So at the moment, we're split 50-50 between answer number 2, 27, Oh, sorry. We've got 60% saying 27, 67% saying 27, and 33% saying 54. So let's do the math. So we've got 0, 1, 1, 0, 1, 1. So that would be 2 to the 1, or sorry, 2 to the 0, which is 1. 2 to the 1 times 1 is 2. 2 to the 2 times 0 is 0. 2 to the 3 times 1 is 8. 2 to the 4 times 1 is 16. 2 to the 5 times 0 is 0. So 1 plus 2 plus 8 plus 16, that's, let's see, 3, 11, 27. 27. Boom. So the point of this is to note that the leading 0 here, is not used or applied, right? Oh, good, we've got 10 people paying attention. That's much better. Excellent. Good. So, in the same way as in the decimal system, if you have any leading zeros, they're kind of ignored and just don't contribute to the number at all. The same thing is true in the binary system. However, one of the things that's interesting about the binary system is that we're often highly concerned with the number of binary digits that we are displaying. You know, it is very, very usual when displaying binary numbers to display 4 or 8 or 16 or 32 or 64 of them. You know, some base 2 number, you may be noticing a pattern here. In these cases, it's usual to sort of backfill the rest of the number with zeros, because the number of bits you're talking about can be just as important as the value of the number itself. But yes. So, there we go. The basic approach, of course, is to compute the sum of the relevant powers of 2. This is the same operation that we've performed, right? You multiply the value of the digit by the power of 2 represented by its position in the binary number. So, Python represents binary numbers in the least intelligent manner possible. It does so as strings. It's like you're literally taking like 8 to 16 times as much memory as you need to store this number. But this is what it does, right? It's like, if you want to see the binary equivalent of any number, you use bin. There you go. Now, there's going to be an assignment upcoming where you're asked to perform said conversions, and you'll have to not use the bin function. You'll have to derive the algorithms from scratch, or, you know, implement it off of the slides, basically. But this is okay for the purposes of demonstration. Note that this is enclosed in quotes and is therefore a string. Like, what the flip, you know? So, you know, doing that, if you want, like, the, like, 7th binary digit, you know, counting from smallest to largest, then you just use negative indexing. But, you know, it's silly. It's silly to store it as a string, and I don't care who knows I think that. But, anyway. So, if we were to write a Python program to do this... Oh, by the way, on that assignment, you're asked to use other base systems other than decimal. So, you know, we're not just asking you to copy and paste this guy given right here. So, if we're converting from binary to decimal, and B is a string of ones and zeros, then basically what we're doing is we're looping through the entire thing, testing to see if B at I is equal to 1, and if so, adding our, basically adding 2 to the power of the position to the accumulator, and then returning that accumulator at the end. It is also possible, like, there's an observation that you might be able to make here about the math, right? Which avoids having to use the exponent operation, which does save some time, right? So let's say we had, you know, 1, 1, 1, 1, right? That's 2 to the power of 4 plus 2 to the power of 3. Or no, sorry. 3, 2, 2 to the power of 1. Oop. Be nice if I could type 2 to the power of 0, right? If we expand out the multiplication, right? It's 2 times 2 times 2, right? 2 times 2 times 2, or not times 2, times 1, and then just 1. And there, you know, if you want to get right down technical, you can throw a 1 term in there as well, right? So one might make the observation that like you could factor out some of these multiplication operations. So you could say this is 2 times something plus 1, you know, if you factor out one of these guys, you end up with this, right? If you factor out another one, you end up with this, and, you know, that's probably as far as you need to go, to be honest. But yeah, you can factor the 2's out. You can actually completely eliminate the need for an exponentiation operation and do this simply with multiplication, which is more, in terms of computations, you save some time. But, you know, that's what this is known as Horner's rule, and this is what it looks like if you were to write it as a function in Python. So we have the same accumulator, right? So rather than, you know, calculate 2 to the power of the position and add that, we say d is equal to d times 2 plus the integer conversion of whatever that decimal is, right? Because if we go back here, if, say, this one was a 0, right, then we would just simply put a 0 in here, put a 0 in there, and it would just be carried through, right? It would eventually be collapsed out of it because it's 0, but, you know, there you have it. Good. So that was conversion from binary into decimal. Conversion from decimal into binary is a slightly more complicated affair. Pardon me for a moment. basically, this is the make-change problem, right? This is like a subset of the make-change problem, except the coins are all of the binary, like the whole binary digits, 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 10, 24, etc., etc., right? Every power of 2 is a coin. And the number that you're trying to convert is the target, right? So what you want to do is you want to see if your largest power of 2 fits inside of this thing, right? If it does, take it out, assign, specify one binary digit, 1 bit there. If it doesn't, assign a 0. Reduce the thing in size until, then take that out and continue on, right? So, if you do that and you take also into account the idea that, you can get to each of the next coins by simply, dividing the entire problem by 2, then you result in this algorithm. There's a question on the current assignment that deals with decimal... Oh, is that on the current assignment? But it doesn't say that we aren't allowed to use bin. Would you say that it's safe to use it n? No. Don't use bin. Do not use it. In fact, I'm going to send a note to the TAs now about that. Or I'll write myself a sticky note to exclude the use of bin on the current assignment. Exclude. Unless the, well, I'll see what the TAs say about it. We'll talk about it. We'll make an announcement on it at any rate. Yeah, sorry I got the timing mixed up. It's interesting, right? It's like the assignments are doubled up basically because this is the summer semester and it, throws me off sometimes. I'm used to teaching this course at like a slower pace. It's, At any rate, so if we were to encode this algorithm, basically, well, let's do an example, right? So topic 6, def. Decimal to binary. Takes a decimal number. So the first thing that you have to do is decide like what the biggest one is, right? So well, now that I'm thinking about it. So because of the way that these numbers work, the algorithm that I just described was going down from the top. Like, you start with the biggest and go to the smallest. It's also possible to start with the smallest and go to the biggest. And that's, slightly easier because you don't need to know when the start point is. So let's do that one instead. But, it's essentially the same algorithm in reverse. So, our binary number is empty while x is greater than 0. B plus equals gonna have to keep a track of gonna have to keep track of an index as well. B is equal to x mod 2. X mod 2, of course, tells us if it's even or odd, which in binary arithmetic exposes whether the last digit is either a 1 or a 0. Pardon me, which is kind of cool. Multiply that by 2 to the power of whatever I is. I plus equals 1. You could probably do with that some other way, but who cares? X equals x integer divide by 2. So there you go. And then we return b. So let's see if this works. Print dec2 bin. Something we know, like 255. Well, something I know anyway. 255 should be 8 ones, I think. Where's my terminal? There we go. Oh. Oh. Oh, I'm sorry. Yeah, no. I messed it up. I'm thinking concatenate. I'm thinking numbers, and I should have been thinking strings. Ugh. All right. String convert that, you stupid thing. And then we want to add the new numbers on that side, so something like that. Me buckos. There we go. Good! And it works. And then if you want to put something fancy at the beginning, like an indication that it is a binary number, there you go. And you can enter large numbers, and it will binary convert them. Bing, bang, boom. Ha! There we go. Yeah, see, using the bin function is too easy, right? You don't actually understand binary. You don't actually understand the process if you're just calling that function, right? So, gonna skip that question because we're getting a little behind. That's basically what I already did. There we go. Except rather than, you know, string converting this directly and adding it to the thing, they're using a big ol', you know, if else. I actually don't need this I anymore because I'm not using it. It's a good point. There we go. Even more compact. Ha! Even more efficient. There we go. So, there we go. So, so that's how you convert things from decimal into binary. So, I'd like to take a moment now to talk about some other base systems which you are likely to encounter if you continue on in your, you know, pursuit of computational excellence. Hexadecimal is one that you're probably going to encounter more, like far, far more frequently than octal, but they're interesting because they form sort of an interesting little dyad. So, binary code, you may have noticed that, like, printing it out, it's unreadable garbledygook, right? It's like, try to parse that. You know? Try to read a number out of that. It's impossible. Like, you know, well, to be fair, you know, for a lot of people, like, reading this number also would be gobbledygook. But, let's say it was a number that everybody can read, like 1 million. That's still, like, very difficult to actually understand what this even is, right? So it turns out that, like, if you're a programmer sitting there at your computer and pressing 1 and 0, like, over and over and over again, just, like, when you need to write a binary number, that's just, like, why would you subject yourself to that when you have other options, right? So, so we have more condensed number formats, which are still have a one-to-one mapping with the binary code itself. Now, decimal is interesting because it doesn't actually have a one-to-one mapping. Like, a single decimal digit does not correspond to a fixed number of binary digits, right? Like, if I were to express, you know, well, you know what, let's do this. For I in range from 0 to 16, print this of I. There we go. Yeah, let's make it include 16. Right? Oh my god. Stop. There we go. There we go. Good. So, you'll see that, well, you know what? Let's print this. Let me print this somewhat more prettily. There we go. So, notice something, right? For the numbers 0 through 9, obviously we need, like, different numbers of binary digits to represent it. That's not interesting, right? That's just expected. What's interesting, in decimal, we need one additional decimal digit when we hit the number 10. But another binary digit is not added at that step. We can represent both 9 and 10 using 4 decimal digits, or 4 binary digits. So, like, the problem is that this means all of, like, if you're expecting a decimal number to tell you what's going on with the bits, it's just not going to, right? So instead, what we have is a format called hexadecimal, right? So hexadecimal numbers basically have one digit for okay. In decimal, there are 10 digits, 0 through 9, right? In binary, there are 2 digits, 1 and 0. In hexadecimal, there are 16 digits, 0 through F. Once you hit 9, after 9, 10, 11, 12, 13, 14, and 15 are represented as A, B, C, D, E, and F. So, a hexadecimal number might be something like decaf, right? Or, you know, face decaf, which is also a palindrome. Incidentally, you can write literals in any base system by using, in Python, by using 0 and then a character designating which base system you're using. So if you want to do binary as well, you can do like that. So that's how you can write like a numeric literal in a different base system. And I think octal is O. Should be. There we go. So, so hexadecimal is very useful because what it essentially gives you is all of the unique values of 4 bits, right? So 2 hexadecimal digits are 1 byte always, right? Whereas that can be up to 3 decimal digits, you know? 4 hexadecimal digits give you 16 bits, right? Or 2 bytes, right? 8 hexadecimal digits give you the full word size of most CPUs that you're using these days. Whereas with decimal, that can be like, I think it's like, you know, 12 or something. So this is just a more compact format for expressing binary data. Hexadecimal is something that you'll see a lot if you take my course on C programming. Yeah, it's used, for example, to represent the values of pointers, and it's even used for that purpose in Python as well. Well, actually, it isn't by default, but there you go. Hex. Octal, very similar to hexadecimal, except it's base 8. So it's a grouping of 3 bits, not 4 bits. It's kind of fallen out of favor. It's not used for nearly as much stuff as it used to be used for. But if you're digging into some old code, then it's possible you'd find octal in there somewhere. But yeah, so 3-bit octal is 3 bits, includes digits from 0 to 7. So yeah. So there you go, base systems. Any questions before we move on to floating point numbers? Oh. Oh, I missed a trick. I should have, like, asked those questions in binary. Oh well. Yeah. So now you know binary. So now you should be able to get you should be able to get the following joke that I'm about to put here on the page. There we go. That's a very old and traditional joke in computer science, but you should get it now. Good. It's okay. You can laugh. It was a joke after all. Come on, I want to see some, like, forced laugh like sarcastic laughing in the chat. Come on. All right, that's fine. So having talked about, thank you, I appreciate that. So having talked about how integers are represented, let's now cast our minds into realms of fractional numbers. So what do I mean when I say fractional? I'm talking about things that would have been called decimal numbers for you in your, in elementary school and high school. These would have been known as decimal numbers to distinguish them from fractions, right? They, fractions have the line, and decimal numbers have the decimal point. Very, convenient system for knowing what numbers are which. However, as we have just demonstrated, decimal numbers are actually things that are base 10. It has nothing to do with the presence or non-presence of a decimal point in actual point of fact, pardon the pun. So, what we're going to be talking about are fractional numbers. That is to say, numbers which have a fractional component. So, more generally, we're talking about real numbers. How do you represent values between 1 and 0 inside of the binary system? Well, let's examine the way that we represent this inside of the decimal system first. And this is like, I'm really not regretting. I feel terrible about having to move the lectures online because I feel this would be much better explained with the chalkboard, but, never mind. This is a typo, by the way. These are supposed to be 10s. So, if we have a number like 20.53, the decimal point indicates the point at which the powers of 10 go negative, right? This is 5 multiplied by 1/10. This is 3 multiplied by 1/100th. So, this is how we represent fractional numbers in the decimal system. The way that we represent fractional numbers in the binary system is precisely and exactly the same. Just, again, modifying what the base number is. So, when we have a number like 11.01, that's, 2 plus 1 plus 0 times 1/2 plus 1 times 1/4, right? So, in the end, this is the binary representation of 2.25. Bing, bang, boom. So this is fine. This is good. But you may have noticed that we skip quite a lot of numbers there relative to the decimal system. So, here is a very important question. How is it that we would represent 0.1 inside of the binary system? Right? And this has a lot of application to that. You guys remember when I gave you that demonstration where if you add 0.1 to itself 10 times, you don't actually get 1? This is the reason, right? This is the reason mathematically and numerically. So, if we wanted to represent 0.1 using 3 binary digits, the closest we could come is 001, or 0.001. That equates to 0.125. This is not 0.1. It is not even that close to 0.1. It's a full 25% off. So, let's add a few more let's add a few more binary digits and see if we can come to a closer approximation. If we have 5 binary digits, the closest we can come is 00011. That equates to 1/16 plus 1/32, which, excuse me, you can see that 3/32 looks a lot closer to 1/10 than 1/8. Yet, we get 0.09375 in the decimal system. So, that's still not 0.1, right? That's still a fair ways off, but it's a closer approximation than using 3 decimal digits. So let's add a few more digits. Let's now use 9 binary digits to represent this number. If we use 9 binary digits, we get 0.000110011. That's 51/512, which equates in binary. Oh my god. I'm messing it up so much. Equates in the decimal system to 0.099609375. Itself a much closer approximation of 0.1 than any of the previous ones. However, still not exactly 0.1. So this is how it goes on forever, in fact. Pardon me for a moment. Sorry, guys. My God. Yeah. So this is how it goes on forever, right? It doesn't matter how many binary digits you add to your representation, you will never be able to completely and exactly you'll never come to at the exact value of 0.1. What you will get is a series of increasingly accurate approximations of that number, right? The reason this happens is 0.1 does not have what we call finite representation inside of the binary system. It's the same problem with 1/3 not having exact representation within the decimal system. Essentially, there's a rule in mathematics. In order for a number to have exact representation within a base system, you have to be able to express that number as a finite ratio between two other numbers in that base system, right? So, you know, all of these numbers, right? All of the numbers that are representable inside of the binary system are, you know, some x over 2 to the power of some y, right? This guy here, this guy has to be expressible as, a whole number inside of the binary system. This has to be true. So, that's why, 0.1, which, does, that's equal to 1/10, right? 10 is not, there's 2 to the power of no whole number produces 10, right? So 0.1 does not have finite representation inside of the binary system. You can basically replace this with b for base, and it's this principle still works, right? So, like, if we were to consider 1/3, right? If we're working with a base system of 10, right? 10 to the y, there's nothing we could rewrite this as that makes this base a power of 10, right? There's no whole number you can multiply 3 by to produce some power of 10, right? Which means that there's no finite representation of 1/3 inside of the decimal system, which you all know because anytime you've had to enter 1/3 into your calculator, you've had to enter 0.3333333333333, as many threes as you can get, because the more threes you add, the more close an approximation you get of 1/3. It's the same bloody problem, right? The same problem precisely. So this is fine. I'm going to assume everybody accepts this principle at this point. All right. So we know that there's no finite representation of 0.1 inside of the binary system. We further complicate this by the fact that you could not represent an infinite number of binary digits even if you wanted to, because computers are finite organisms, right? Or they're not organisms, they're machines. A computer is a finite device. While it may have billions and billions of bits available for your pleasure, perhaps even a million bits. Who knows? Actually, it's interesting. Apparently, according to British use of the term, British English, billion meant a million, and then in American English, a billion meant 1,000 million. And because Americans were the culturally dominant ones, when billion started to be a number you had to worry about, that's how that worked. But anyway. So anyway, you might have, more bits, you might have so many bits that it would take you your entire lifetime to count them all. But that's still not infinity. And it turns out that, for most purposes, you don't need the exact representation. A close enough approximation of this is fine for most purposes. So this is essentially how we represent these numbers. The way that computers represent these types of fractional numbers is using a format known as floating point. So floating point numbers are standardized. A lot of you guys, you're primarily a sort of outside of the crowd that would know this kind of stuff, but this is basically an engineering problem. Engineering standards organizations are a very, very, very important facet of human civilization in the modern era. One might even say that engineering standards organizations have produced the modern world to a large extent. Do not underestimate the power of standardization and standardized parts. We had a problem. Given the physical restrictions of numbers inside of computers, and given that we probably want to shoot for representations that fit inside our, our commonly used word sizes, 32 bits and 64 bits, how do we divide those bits up so that we have a, reasonably accurate representation of fractional numbers? We also have to fold in the idea that we're not just representing a fractional number when we're representing a real number. We also have to represent the actual magnitude of that number, right? Floating point notation is essentially a derivation of scientific notation. So if you've never run into scientific notation before, it's like if you were to express, for example, the universal gravitational constant right? The universal gravitational constant is expressed in the following manner, right? You have some number which has a fractional component and only one digit before the decimal point, multiplied by some power of 10, right? This reduces the amount of information that you need to know to accurately represent the number to the fraction itself and whatever the exponent is. The times 10 can be assumed, right? This is scientific notation. Floating point representation does exactly the same thing, except, of course, everything is in binary. So we've got a fractional component, right? And we have an exponent component, and we also want to leave one bit aside for the sign, right? So the question is, how do we divide up these bits so that we get reasonable accuracy? Well, it's been standardized by the, I always mess up the acronym, but International Electrical Engineering something. What does IEEE stand for? Geez. Something I should know. Institute of Electrical and Electronics Engineers. So the IEEE publishes all kinds of standards documents that set all of these things as fixed values. Basically, it's beyond foolish to manufacture any device that's not IEEE compliant. Basically, the only reason our computers can talk to each other over the internet is because they all assume the same things are meant by floating point numbers, for instance. Like, if I were to write a number, send it to you, and your computer thought it was a completely different number, those are not computer systems that can communicate with each other, right? So standardization is very important. At any rate, so floating point numbers, right? Following the IEEE standard, the fraction component, the part that we've been talking about that can't completely accurately represent 0.1, we give it 52 bits with a leading one, with one bit before the decimal point. So that's quite a lot of precision, right? That equates to approximately 16 decimal digits. So if I were to take a number like 1/10, represent it with 60 bits of precision, you'll see that how it's actually represented is you have 0.1 up to around the 15th or 16th digit, and then you get essentially randomness, right? This randomness is generally considered to be an acceptable margin of error on these calculations. every once in a while, if you're performing particular types of repeated calculations, you can have this error show up, right? This can accumulate and cause problems. But for most cases, this is good enough. Yeah. In addition, 11 bits are used to represent the exponent. So we can shift this up and down by 2 to the power of some number that can have at most 11 bits. Also, this is one of those bits will include a sign, so you can have negative ones as well. So this results in a maximum representable value in floating point arithmetic of 1.798 approximately times 10 to the 308th power inside of floating point arithmetic, and a smallest positive number, of 2.23 times 10 to the negative 308 in decimal arithmetic. So if you think about the sheer scale of these numbers, right? Let me just pull up current estimate for the number of atoms in the universe. So, current estimates for the number of atoms in the observable universe is 10 to the 78 to 10 to the 82, right? So, we are talking, more than 200 orders of magnitude more than that, right? Now, it's not just a range thing, it's a precision thing. You can't you can represent a number of that magnitude, but you can't you can't represent each one of those individual atoms with one of these numbers, obviously, right? Because you don't have that kind of precision. So yeah. So in general, the more bits that you have in your fractional component, the more precision you can express with the number. The more bits that you put in the exponent, the more range you can express. This was a solution that was arrived at by the IEEE, which is in wide use. So there you go. There are some interesting consequences of this, though. Because the precision of floating point numbers are limited, it's possible to use them to, it's possible that you get some additional mathematical artifacts with them. So if you take a number that's sufficiently large, right? If you add 1 to it under, integer arithmetic, you get what you expect. However, if you add 1 to it under floating point arithmetic, you do not get what you expect. This plus 1 is gobbled up, right? So, in effect, if you have a counter running that's using a floating point floating point representation, and you let that counter run long enough, it will lose the ability to keep track of its own incrementation and thus be stuck on some large value forever. Which is like an interesting little factoid about floating point representations, and that's an indication of why you should be using integer arithmetic and not floating point arithmetic. The general coping strategy for floating point arithmetic in general is to use integer arithmetic wherever possible and only use floating point when you need it. But yeah. So, Okay. So I think I need to give my voice a 5-minute break right now. So I'm going to call a break until 11:10, at which point we will resume the lecture. Okay? I'll see you guys in 5 minutes. return. Okay, folks, this last hour of the lecture may get interesting, because as I was like walking around the house and drinking water and things, I noticed that a bulldozer with a mechanical jackhammer in its scoop was coming down my street, and I was like, oh, don't stop at my house. And it's like, oh, it stops at my house. It's like, yes, it seems like some construction guys are going to be doing some road work, like across from my house. I don't know if they're going to hold off for the next 50 minutes. So if there is a jackhammer sound in the background, I hope it doesn't interfere too badly with the lecture. There's really nothing I can do about it, unfortunately. That's rather unfortunate. We'll see how it goes. Okay, where were we? Ah, yes! Floating point. So I've done a lot of like talking about how, floating point is, not as accurate as you might think it is and should be avoided and all of that. But the question remains, how does one go about avoiding it? Well, this is your floating point survival guide. So, number one, and I've talked about this before, but the first thing that you have to understand about floating point is that it's absolutely crucial that you never perform exact equality comparison with it. Right? So, something like this, there's a point at which this is no longer going to be the case. Right? And the point at which equality comparison is going to fail for you is essentially unpredictable, since it involves all of these details way down, low down in the representation, right? So, the safe thing to do, take one number and subtract it from the other, right? Take the absolute value of that and check to see if it's less than some small threshold. The threshold should be small enough that it excludes anything that you don't want to be included, but it should not be so precise as to exceed the precision of the difference itself. Otherwise, it's useless as a test. So, this is your alternative to equality comparison with floating point numbers. Salat! Salat. So that's number one. Don't use exact equality comparison. Number two, there are a couple of libraries which you can use which allow you to get around certain floating point problems. When you use these libraries, you're doing it at the expense of memory and runtime. Basically, you're trading memory and runtime for greater precision. But if precision is what you need, then so it goes. So, from decimal, import decimal, right? Actually, as D. There we go. So, decimal 1 divided by decimal 3 is, you can see, a very precise decimal number, right? This is more precise than you would get with regular representation. So, decimal 1 divided by decimal 10 is 0.1. The idea with the decimal library is that you would get the same errors as calculations by hand. By default, 28 fractional digits are kept, and the precision can be configured. The problem with the decimal library, however, is that it's very sensitive to the thing that gets put into it. So if you try to convert a floating point number to decimal, to the decimal library, it's just going to give you, well, this is a floating point number, and this is what it is. In order for the decimal library to work, you have to perform the arithmetic itself inside of it, right? So, if you want a value like, 0.1, you either have to express it this way, calculate it from other numbers that have already been converted to the decimal library, or provide the number as a string. That also works, right? So that's the decimal library. That's a perfectly acceptable option. And, if we add 3 of these together, then equality comparison does work. Capici? So that's the decimal library. Next, we have the fraction library. So the fraction library is about what you would expect as well. Rather than expressing decimal numbers, it expresses fractions. So, if we from decimal import fraction as f, incidentally, the as f here just allows me to rename the class that I'm importing from the library so that I don't have to write out like decimal, 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 decimal all the time. I can just refer to it as a single letter. Oh, import from fraction. Fractions. There we go. So, fraction 1 over fraction 3 is 1/3. It's like numerator, denominator. You can also enter it that way. So it's like fraction 7/19. There you go. 7/19 divided by, 1 over 4. 28 over 19. Fraction arithmetic. The same as you would have done in high school or elementary school. Fractions is like grade 5, I think, right? I think I'm getting that right. Unless the government has completely destroyed the math curriculum since I last checked, which is entirely possible. So yeah, so that's the that's the fraction library. So here are your coping mechanisms. So the first thing, it's kind of like reduce, reuse, recycle. The first step is to try to use less float. So to avoid using float and use integers instead, you can actually sometimes just move the decimal point and everything works out. Like, for example, if you're doing something with money, right? We normally represent money as like 350, 3.05 or 3.50. We don't have to, right? That involves like decimals, but we don't have to do decimals. If we count in cents rather than in dollars, right? Then, assuming you're not doing some highfalutin financial transaction that requires fractional cents, you can do all of that with integer arithmetic rather than floating point arithmetic. Same idea, converting from meters to millimeters, or from feet to, well, feet to inches is a little bit different because it's not, metric. But anyway, so you can manipulate the numbers a bit to produce an integer system rather than a floating point system. This is in fact what we did with the make change problem. You can use decimal or fraction standard libraries instead. They are slower, particularly for large or small numbers, but more precise. You can use a library for interval arithmetic with float. This gives safe lower and upper bounds, taking twice as much time in memory. You can use a problem-specific library or check literature for algorithms with known numerical properties. If you're trying to perform a floating point operation, it's possible that this problem has already been solved in a library, so you should use that library. You can use symbolic computation as in computer algebra systems instead of a programming language. Well, that only works for very specific types of problems. When using float, never, ever, ever, ever compare for equality directly. Check result within tolerance. If you do it, you'll make me very sad. Very sad. Every time you use direct equality comparison on floating point numbers, God kills it. Uh-oh. Oop. Am I okay? Am I coming through? I just got a message that OBS kicked out momentarily. Okay. Seems like we're okay. Scanning back through the video. Yeah. The word that was cut out was kitten. God kills a kitten every time you use direct equality comparison on floating point numbers. All right. You're fine? I'm fine? I'm good? Okay. Yeah, I always get a little bit jumpy when when OBS kicks me out, cuz in previous semesters, I was having this horrible problem, when we were doing primarily live streaming, that it would kick me out every half hour or so, and I'd have to wait 5 minutes for it to reconnect. And it was so interesting because it was I had an interesting problem with my internet in that my signal strength was too strong. So if signal strength inside of these coaxial cables, right? It's an analog signal. So it's the signal strength amplitude has to be within a certain band. If the amplitude is too low, then it's inside of the noise floor, so you can't transmit data effectively. But if it's above a certain amplitude, then the analog to digital converter can't pick out the individual bits, because it's like clipping. It's like the clipping problem with audio. So that was what was happening, and it was causing all kinds of desynchronization problems. But I got that fixed, but that's why I'm jumpy about those sorts of things, because for me, getting that little notification that OBS disconnected has in the past been a much bigger problem. Also, I don't know if these people who are digging up the road next to me are gonna hit my internet line or some goddamn thing. Ugh. I hate people. Why don't people just leave me alone? Honestly. Anyway. So, any questions about floating point numbers before we move on to approximation algorithms? Okay. I'm going to assume no questions then. So let's talk about approximation algorithms. So, remember this guy? Remember this from the first class? The bisection method, where we test to see if the function is above or below the x-axis, and then we move the bound in depending on the result. Remember that algorithm? We can now answer a question. Can we compute the exact x-intercept by taking e equals 0? Right? So if we say that the epsilon, the precision, is 0, can we get an exact x-intercept? Now we know that we can't, because we're dealing with floating point arithmetic. In floating point arithmetic, there is some smallest number that can be represented, right? You can almost think of floating point numbers as operating like electron charge. Each electron has a charge, the charge quantum, and there are no charges that exist that are not quantized in that manner. You can think of floating point as being in the same vein. So no, if a and b are rational, and the x-intercept is irrational, then it will never be reached. Even if you had even if you were using, in some kind of infinite precision representation that doesn't exist, you would never actually reach an irrational number from a rational one. Like, for example, root 2, which is very easy to produce. So, so in Python, let's explore this one a bit, eh? In Python, functions can be passed as arguments. Can I copy this in? Yay! So, we can write, this is very similar to the function that we wrote, the first function that we wrote. So this is just a direct implementation of that algorithm, right? Taking the function f as an input and calculating the x-intercept given a range a and b and an epsilon. So let's say that we had, print x-intercept, and let's use our new knowledge of anonymous functions. So let's say lambda x times x plus 4 from 0 to 100 to precision 1 to the power of -8. And let's run this bad boy. Are we in an infinite loop here? Oh yeah, because I don't have the indentation correct. There we go. There we go. So, did I mess up the formula? Yeah, it's supposed to be negative here. Sorry. There. So, our approximate x-intercept for the parabola x squared minus 4 is approximately 2. as we can see here. We can ramp up the precision here, right? We can ramp it up even further. But past a certain point, the thing just hangs. So, to see why it's doing that, let's print these values and take a look, shall we? So, print separator, print a is equal to the value of a. I suppose I could also do this in Python Tutor, but, you know, whatever. I'm already doing it in terminal. So starting at the top here, you know, we divide, you know, we follow this algorithm all the way down till we hit, you know, we start hitting reasonably close approximations of 0 for f at m, or like we're getting closer anyway. At any rate, f at m is starting to be negative and positive, right? The closer it gets, right, the closer a and b get, until a certain point, right? Closer, 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 until we hit a certain point, right? We've actually, in this case, exactly hit f at m is equal to 0. So if f at m is equal to 0, then we move m to a, right? But this midpoint that's being calculated, because it's being calculated via the sort of standard division operator, this, right, plus that, divide by 2, is equal to a. So we're reassigning, it's similar to the bug that we were seeing last week, where we were continuously reassigning a value to a value that's the same value. This is expecting the values to change, so that sticks us in an infinite loop. And that is how the cookie crumbles in this particular instance. Now, this is despite the fact that we have an actual rational number that is the expected result, right? If we check, like, because essentially what this function computes is the square root of this number here, right? So if we change this to a number that has an irrational square root, we might get something slightly different. So, we get basically the same phenomenon, right? Except this time it's working, well, it's working pretty much exactly the same. So, yeah, so that's why this doesn't work at that level. Good. So it's approximate, and if you demand more precision than is possible, you're going to cause problems. That's the take-home message. So let's talk about another algorithm. Approximate square root. So it turns out that calculating a square root is actually reasonably difficult. Like, anybody in the crowd actually try to calculate a square root rather than just asking for it from your calculator? Like, I don't know about like you guys or where you went to school, but for us they didn't even bother teaching us how to calculate square root. I found out later that you have to use like binomial theorem to get there. So it, like, at least requires algebra. So it's useful to have an algorithm which approximates the square root of a number n. So given some number n, a is an approximate square root if n is between a squared and a plus 1 squared. So we're kind of going for, like, the floor, right? We're going for, like, it's like Price is Right rules. The nearest without going over the nearest whole number to the square root without going over the square root. That's what we're trying to calculate here. One way to compute this is by linear search, or exhaustive search, also known as brute force algorithm. We set a as equal to 0, while a squared plus 1 times a squared plus 1 is less than n. We increment a, otherwise we return a. Or when we're finished that, we return a. Pardon me. This will eventually find you your correct result, of course. But there's got to be a better way. Or I guess we'll... we don't need to trace this program. It's too simple. So the question for n greater than 0, how often is b executed, right? Approximately the square root of n, right? You need to execute this loop once for each number that you're iterating through. So if you're calculating large square roots, this is, like, not a very useful way of going about it. So, good. Now, here's an interesting thing, right? You remember the binary search algorithm? You remember how that relied on our numbers being sorted? Well, one thing about the numbers, like, that you count, starting at 0 and counting by 1, is that all of those numbers happen to also be sorted. So, let's suppose we have an a and a b, such that the root is between a and b, right? So, essentially, we're renaming a plus 1 as b, right? And we're going to perform our division algorithm. We repeatedly replace either a or b by a plus b integer divide by 2, such that the above holds. That is to say, a squared is less than or equal to n and b squared is greater, until a plus 1 is equal to b, and then a is the approximate square root. So, here is a different algorithm. Let's actually implement this one, shall we? So, def bin square root n. We have an a equals 0. We have a b equal to n. Sure. Because the square root of a number is going to be, well, we can say n plus 1. The square root of any whole number is going to be no greater than the number itself, unless it's, like, less than 1, but, you know, it's not, because I already excluded that. While a plus 1 is not equal to b, c is a plus b divide by 2 if c times c is less than or equal to n, a is equal to c, else b is equal to c, return a. So let's see how this operates. Print bin square root of something like 93. And while we're in this loop, let's just also print out what's going on. Where's my terminal? There it is. Ah. Friggin', yeah. There we go. Oh. Yeah, that makes sense. There. So, we start with this, right? Oh, you know what? Let me print the target. So the target here is 9.64, right? So you can see via the bisection method, we are gradually approximating this value, and we do eventually reach it. Bada boom. So there you go. So in order to refine this algorithm, make it slightly more efficiently, make it run more efficiently, you know, binary search is already pretty efficient. But we could, in theory, refine the search range, right? The larger the search range is, the more iterations it's going to have to go through to find the approximate square root. So, it's actually, if we, for example, examine the output of this, right? We are executing this loop 1, 2, 3, 4, 5, 6, 7 times, right? That's not too much savings over the previous method. But that's because we're sort of taking a wild guess as to what the upper bound is going to be, right? Another way that you can do this is you can calculate you can use a loop to determine what a good upper bound for b is going to be in this, according to n. So, while b times b is less than n, b equals b times 2. Let's examine the difference. So in this case, and let's just make a mini version of this right here. Let's use a different character to indicate it's a different loop. Right? So, we execute this loop 4 times. It's only got the one statement going on in it, so it's a very fast loop, right? And that allows us to only have to execute the larger loop 4 times, as opposed to the 7 that we had before. So this is again a net savings in runtime, relatively speaking. Good. So, the first loop sets b equal to 2 to the power of k after k executions. The second loop halves the interval b minus a at every execution until a plus 1 is equal to b, hence also taking k executions, right? Notice, right, number of loop iterations the same in both cases, right? So, hence, each loop takes k equals log base 2 of b to execute. So, the number of executions that we require is approximately equal to log base 2 of the square root of n, right? So, there's some fancy approximations that are going on here that we're going to talk about after Pythagorean triples. I'm just going to talk about it now. So, the question that sort of arises at this point is, how do we come up with some kind of objective measure of the runtime of an algorithm? Because according to this analysis at the bottom of the slide here, right, the fact that we have reduced, like, it basically doesn't consider the fact that the loop is being run twice, right? It's like, oh, well, this and that, it doesn't really matter. This is proportional to log base 2, right? Log base 2 of the square root. So this sort of gets into a manner of characterizing algorithms which we call big O notation. So the object in general, to characterize the runtime, let's talk about runtime specifically here. The object, the thing you're shooting for to characterize the runtime of an algorithm is to come up with some kind of mathematical formula that describes the runtime given the size of the input, right? Size of the input could mean many things. Typically, it means like the number of elements in a list or a tuple. In this case, it means the like magnitude of the input, right? At any rate, you want to derive some kind of equation, right? Now, the equation that you're likely to derive, let's consider a pseudocode algorithm with 3 while loops, right? It's got some statements, you know, let's say it's got statement A, statement B, statement C, and statement D, right? Mathematically speaking, also, let's assume that this loop runs, let's say each one of these loops run n times, yeah? The number of times D will be executed is n cubed, right? Because it'll be run, this loop is run once for every iteration of this loop. These loops are run once for every iteration of this loop. So in the end, D is run n cubed times. And you multiply that by the amount of time it takes to run D to get how long that takes. Similarly with C, you have C times n to the power of 2. Sorry, I meant power here. Plus B times n plus A, right? Plus operating system. you know, whatever time it takes the operating system to do its thing, right? That's like the formal equation, right? Big O is an approximation of this that characterizes the algorithm. So the question asked by big O notation is, okay, so we have this long complicated equation. Which term in this equation will come to dominate this equation as n grows, right? Which is kind of an it's kind of an interesting mathematical question, right? It's like, which one of these contributes the most to n, you know, as n becomes bigger? So you can imagine, you know, if n was equal to, you know, 2, then it's, you know, d times 8 plus c times 4 plus b times 2 plus a plus os, right? While this term certainly has a lot going for it, it comprises probably around half of the runtime. That's not like overwhelming dominance. Consider, however, like 10, right? D times 1000, C times 100, B times 10, 8, and like you can see that's a much greater ratio, right? And that only increases the larger n gets, right? As n, like if n was 1,000,000, you would see that like D would overwhelmingly control, like this term here would overwhelmingly control the runtime of the algorithm, right? So, to approximate something as, like, to come up with a big O approximation, we basically say we're going to take the highest term, right? We're going to ignore the fact that any smaller term exists. And in addition to that, we're going to drop the constant. And the reason we drop the constant is the amount of time it takes to execute D is very, very highly dependent on your computer system itself, right? So if your computer system is very slow, D will take a long time. If it's very fast, D will not take very much time at all. It does not tell us, again, it doesn't really give us a broad-based assessment of how well the algorithm will execute. So, and it's not really good for coming up with a system of categorization. This, like big O, is a system of categorization, right? So we say that an algorithm like this has big O n cubed complexity. That's where the notation derives. So, if you take algorithms of different complexities and you were to plot them, as n increases, basically you end up with a hierarchy of good to bad runtimes, right? So, good runtimes are things like log base 2n and square root of n. And like these are very good algorithms because as n grows, they do not grow very quickly. They are fast even for large n. Linear algorithms, still considered quite good, right? N log base 2n, so n log n, that's better, but, you know, you're starting to creep up there. Then you've got n squared, n cubed. These are starting to get worse. And after this, you've got even worse algorithms, like the dreaded log, big O of 2 to the power of n. This is where you're getting into non-polynomial algorithm territory because, you know, this is a polynomial, right? This is non-polynomial. That's where it derives from. And then, like, God help you if you're in a situation like this, right? It explodes so quickly you can't process hardly anything. Make sense? So yeah, so that's big O notation. Any questions? I don't think I can really start the Pythagorean triples example. It's pretty long, and we've got like 4 minutes left in class. So I'll take questions for the next 4 minutes, and then we'll be on our merry way. Hey, questions. Actually, while you're doing that, I'm oh, okay. Never mind. I thought I heard something that I had to attend to, but it turned out I was wrong. Nose-blowing ASMR. Unrelated to content, is the test able to be done remotely, or will attendance in the testing room be taken in some way? Oh, yeah, no, you absolutely 100% must be in the testing room, or else we will not mark your test. Yeah, we are taking names, we are making a list and checking it twice, and if you, like, you are not permitted to write the test remotely. We will know. We will be keeping track. And the TAs and myself are going to be invigilating. I've got 3 TAs and around 60 students, so each TA only has to keep on top of 20 of you, which is actually very, very reasonable. So there will be no skullduggery in my testing room. We will be keeping very close attention to, like, watching what you're doing with your computer and making sure you're not, communicating with people and stuff like that. Oh, yeah, there's another thing about the test. Disable all messaging apps. No email, no messaging apps. Eh? No Discord. If we see anything, it's it's a warning and then a citation. Are spring exams usually written within 3 days of the last day of classes? Yes, usually. Like, normally, it depends on when the last day is, but normally, yeah, it's definitely within that week. Definitely within that week. How about Google something? Is that allowed? Googling for reference is allowed. The internet is permitted as a reference, source of reference, but you are not permitted to communicate with people. We will be watching. If you're unsure about whether or not something constitutes academic dishonesty, then just don't do it. If you just don't do it, then there's no possibility. Are lecture notes permitted? Lecture notes are permitted. Yeah. Basically anything on Avenue is permitted. Okay, well, I'm going to sign off here, folks. Have fun in your tutorials today, and see you next week.